Alright, in this video we're going to be looking at arithmetic with functions. So the sort of algebraic operations that you can perform with functions, ways of combining old functions to get new ones. Right? We'll be building up some examples of basic functions in the next few videos. And once we have those basic functions in mind, the operations that we introduce here will tell us how to take those basic functions and combine them to get more interesting examples. Okay? So the first thing you can do with a pair of functions is you can add them together or you can subtract them. So how do I define the sum of two functions? Well, the way I define any function is I tell you what it does with a given input. So I need to tell you, so the function f plus g, the way I tell you how it works is I tell you what it does when you plug an x value in. And this is defined in the most obvious possible way. The sum of the two functions is just given by the sum of their values, so f of x plus g of x. And subtraction is defined in exactly the same way. F of x minus g of x. Okay. Now, notice that if we want these things to be defined, right, I need to know something about the domains of f and g, because f of x needs to be defined, g of x also needs to be defined, and that means that we can only consider values that are in the overlap of those two domains. And so, that means that there certainly will be situations where you can't possibly add the functions together if the domains don't overlap, right? So what you need is you need x to be in the domain of f, and you need it to be in the domain of g, right? You need it to be in both. One way you often, if you're familiar with set operations, you might talk about x being in the intersection of the two domains. We're not worrying too much about that in this course, so maybe I won't get into that. But you could talk about this in terms of intersections of sets, if you so desire, right? So x has to belong to both sets, and so that's something you got to keep in mind, right? So if I had, if f of x was, I don't know, let's say f of x is the square root of x, which is only defined for x bigger than or equal to 0. Let's say g of x is, I don't know, the natural log of minus x. Okay. Well, the natural log only works on positive numbers, and if I put a minus sign out front, that turns any positive number into a negative. Turns any negative into a positive. So this g of x is only going to work if x is, let's say, negative, right? So if somebody asked me to work with these two functions and add them or subtract them, I'd have to say, well, buddy, you're out of luck because I can't add them together. Well, I could add them, but I would get a function that isn't defined for a single value, right? Because the inputs for f of x only work for x bigger than or equal to 0. The inputs for g of x only work when x is less than 0. There's no x that satisfies both of those conditions, and so I would get a function that simply is not defined. I mean, not at any point, right? So when you're adding functions, you got to make sure that there's at least a few points that are common to the two domains, or else this doesn't even make sense. The same rule, of course, goes for multiplication and division. As far as the domain goes, and the way you define these, well, you can probably guess that the definition is exactly the same. If I want to define f times g, I can define that as f of x times g of x, so you simply multiply the two values. So if you want to multiply functions, you multiply the values. Similarly, if you want to do a quotient, if you want to divide two functions, f over g, you divide the values. Okay. And of course here you have to be careful. There's an additional restriction on the domain. We can't divide by 0, so we have to throw out any x values where g of x is equal to 0, right? So if I had, for example, let's say h of x is x over, let's say, the square root of, I don't know, 1 minus x, right? Well, I need the square root to be, the number under the square root can't be negative, so that means that 1 minus x has to be greater than or equal to 0, so x has to be less than or equal to 1. But actually I can't let it be equal to 0 either, because then I would be dividing by 0, so in fact it's got to be strictly less than 1 because it's in the denominator. So you got to watch out for things like that. One special case of multiplying functions, if f of x equals c is a constant function, so we get this value c for every x value, right? So c is some number. Then I could define c times g, and you get it exactly the way you expect. You do c times g of x. Okay, so function arithmetic is pretty much exactly what you would expect. There are no surprises there. The other way that you can combine functions is composition, right? And composition is the one that takes a little bit of getting used to. And so this is when you are plugging one function into another, right? So somebody gives you functions f and g, and you can define. So the notation is this circle, f o g. We often read this f o g, or f composed with a g. And the way you define this guy is you first evaluate g of x, and then you plug that into f. And by the way, there are two different ways you can compose these functions, right? With addition, subtraction, well, subtraction, I guess the order matters. Addition and multiplication, the order does not matter. With composition, the order definitely does matter, right? So, for example, if f of x equals, say, x squared, and let's say g of x equals, let's do e to the x, right? So f composed with a g, so f of g of x would be, well, I do f of e to the x, and so that means basically, this function notation always says you take whatever this input is and you do the operation to it. So I need to take e to the x and square it. So this is e to the x squared, and if you know your laws of exponents, you know that that's e to the 2x. Whereas if I did g of f of x, I'd be doing g of x squared, which means take x squared and plug it into the exponential function. And so here I get e to the x squared, which is not the same function as e to the 2x. So you've got to pay attention to order when you're composing functions. And as far as domain, well, if you're doing something like f composed with g, obviously, first of all, g has to be defined at x, but then f has to be defined at g of x. So sometimes you gotta watch out for domain on these things as well. Okay. Now, one of the skills that you're going to need later on is the ability to decompose a function. Now, there's not a unique way of doing this. There's a few different ways that you could try to do something like this. But you often have to identify when you're dealing with composition of functions and how to break things apart. We're going to see that this is essential for doing things like applying the chain rule. So somebody gives me this function here. Okay, 1 over the square root of 3x plus 2. I want to break it up. Well, there's a few different ways I could do it. I could take f of x to be 1 over the square root of x. I could take g of x to be 3x plus 2, and then we could see that if I take g of x and I plug it into f of x, f of g of x, I do indeed get this big F. I could take f of x to be the reciprocal function, 1 over x. I could take g of x to be square root of 3x plus 2. That would also get the job done. Of course, this I could even break up further. I could break this up into, the square root function composed with the 3x plus 2 function. I could break it up into those parts, right? So I could even break this up into 3 pieces if I want, right? So there's not always a unique answer, but you want to be able to know how to break these things up. If you have a complicated function, you want to know how to be able to break it up into simpler functions. Okay. The other place where you might see function composition is this idea of transformations. I'm just going to very quickly mention this because it's something that you've probably seen before and you'll run into it as we move forward. So this has to do with kind of how some basic compositions affect the graph of a function, right? So if I give you, say, f of x, and let's say the graph, I don't know, the graph looks like that, right? You can consider things like f of x minus a, right? And that's the same picture, but you've shifted things to the left, right? So you've done this composition. X plus a, you shift to the right. You could do things like f of like 3x. This gives you a sort of a stretch. Right? Things get stretched out. Not a composition per se, but you could also do things like, say, f of x plus 2. Well, that takes your original picture, shifts it up by 2 units. So some of the transformations you write as function compositions, or of course as simply a sum of 2 functions. You could also, oh, I've lied, haven't I? Did anyone catch my lie? This is a vertical stretch. I should have the 3 outside. Not the same thing, by the way, as f of 3x. That's a horizontal stretch. Alright, I haven't finished my coffee yet this morning. F of 3x would look more like that. Okay, stretched horizontally rather than vertically. Right. So all these graph transformations that you probably encountered in high school, each one can be thought of as a function composition, or in terms of a multiplication of 2 functions, sum of 2 functions, difference of 2 functions. If you've seen this before, it's a useful skill to kind of be comfortable with these transformations, because it means that, you know, if you know a few basic graphs, it's easy to figure out how slightly more complicated graphs are obtained from the basic ones using transformations. Okay, in the next video we're going to talk about polynomials.